Welcome to our exploration of atoms and nuclei, the fundamental building blocks of matter. Atoms are the smallest units of ordinary matter, making up everything we see around us. Each atom consists of a central nucleus surrounded by a cloud of electrons. Understanding atoms is essential because they form the basis of chemistry, physics, and even biology. In this video, we'll journey from the basic structure of atoms to the mysteries hidden within their tiny nuclei. Let's begin by looking at what exactly makes up an atom and why they are so important in the universe. Atoms are made up of three main types of particles: protons, neutrons, and electrons. The protons and neutrons are tightly packed together in the nucleus at the center of the atom, while the electrons orbit around this nucleus in various energy levels. The number of protons in the nucleus determines the element, while the number of electrons influences the atom's chemical behavior. This structure is what gives each element its unique properties and allows for the vast diversity of matter in the universe. The concept of the atom dates back to ancient Greece, but it wasn't until the 19th and 20th centuries that scientists began to uncover its true nature. Early models imagined atoms as solid spheres, but experiments by scientists like J.J. Thomson, Ernest Rutherford, and Niels Bohr revealed a much more complex structure. Their discoveries showed that atoms have a tiny dense nucleus, and that electrons move around this nucleus in defined paths or clouds. These breakthroughs laid the foundation for modern atomic theory. The heart of every atom lies the nucleus, a compact region containing protons and neutrons. The nucleus is incredibly small compared to the overall size of the atom, but it holds almost all of the atom's mass. The discovery of the nucleus was a pivotal moment in science, as it explained why atoms are mostly empty space and why they have such concentrated mass at their centers. The forces that hold the nucleus together are among the strongest in nature. Protons and neutrons are the two types of particles found in the nucleus. Protons carry a positive electric charge, while neutrons have no charge at all. The number of protons in the nucleus defines the atomic number and determines which element the atom represents. Neutrons, on the other hand, help stabilize the nucleus and can vary in number, leading to different isotopes of the same element. Together, protons and neutrons are known as nucleons. Electrons are tiny, negatively charged particles that orbit the nucleus in specific energy levels or shells. These energy levels determine how atoms interact with each other, forming the basis for chemical reactions. When electrons move between energy levels, they absorb or release energy, which can be seen as light or other forms of electromagnetic radiation. The arrangement of electrons in these shells is what gives each element its unique chemical properties. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. This means they have different atomic masses but behave similarly in chemical reactions. Some isotopes are stable while others are radioactive and can decay over time, releasing energy. Isotopes have many uses, from medical imaging to dating ancient artifacts, making them an important concept in both science and everyday life. Atomic nuclei are unstable and can spontaneously change into other elements by emitting particles or energy, a process known as radioactivity. This phenomenon was first discovered by Henry Becquerel and further studied by Marie Curie. Radioactive decay can produce alpha, beta, or gamma radiation, each with different properties and effects. Radioactivity has both beneficial uses, such as in cancer treatment, and potential dangers like nuclear accident. Nucleus is held together by the strong nuclear force, one of the four fundamental forces in nature. This force is much stronger than the electromagnetic force that repels the positively charged protons from each other. Without the strong nuclear force, the nucleus would fly apart. Understanding this force is key to explaining why nuclei are stable or unstable and how nuclear reactions occur. Nuclear reactions involve changes in an atom's nucleus and can release enormous amounts of energy. There are two main types: fission, where a heavy nucleus splits into smaller parts, and fusion, where light nuclei combine to form a heavier nucleus. These reactions power the sun and nuclear reactors on Earth. Understanding nuclear reactions is crucial for harnessing nuclear energy and for understanding the processes that fuel stars. Fission and fusion are two opposite nuclear processes. In fission, a large nucleus like uranium splits into smaller nuclei, releasing energy and neutrons. This process is used in nuclear power plants and atomic bombs. Fusion, on the other hand, occurs when small nuclei like hydrogen combine to form helium, releasing even more energy. Fusion powers the sun and holds promise for future clean energy sources if we can control it on Earth. Nuclear energy has many applications in our world today. It's used to generate electricity in nuclear power plants, provide medical treatments like cancer radiotherapy, and even power spacecraft. While nuclear energy offers a powerful and efficient source of power, it also comes with challenges such as radioactive waste and safety concerns. Balancing the benefits and risks is a major focus for scientists and policymakers. Over time, scientists have developed several models to explain the structure of the atom. The earliest was Dalton's solid sphere model, followed by Thomson's plum pudding model, Rutherford's nuclear model, and Bohr's planetary model. Each model improved our understanding, leading to the modern quantum mechanical model, which describes electrons as existing in probability clouds rather than fixed orbits. Quantum mechanical model is the most accurate description of the atom we have today. Instead of fixed orbits, electrons are found in regions called orbitals, where there's a high probability of finding them. This model explains many properties of atoms, including why they emit or absorb specific wavelengths of light. Quantum mechanics has revolutionized our understanding of the microscopic world. Electron configuration refers to the arrangement of electrons in an atom's energy levels or shells. This arrangement determines how atoms interact and bond with each other. The periodic table is organized based on these configurations, which is why elements in the same group have similar chemical properties. Understanding electron configuration is essential for predicting chemical reactions and the behavior of elements. Periodic table is a powerful tool that organizes all known elements based on their atomic number and electron configuration. Each element's position tells us about its properties and how it will react with other elements. The periodic table is essential for chemists, physicists, and anyone studying matter, as it provides a roadmap to the building blocks of the universe. Atoms combine with each other to form molecules through chemical bonds. The main types of bonds are ionic, covalent, and metallic. These bonds result from the sharing or transfer of electrons between atoms. Chemical bonding is what allows atoms to form the vast array of substances we encounter every day, from water and air to complex organic molecules. When atoms gain or lose electrons, they become ions, charged particles that play a crucial role in chemistry and biology. Ionization is the process by which an atom becomes an ion, either by losing electrons to become positively charged cations or gaining electrons to become negatively charged anions. Ions are essential in processes like electricity conduction and nerve signaling. Every atom is defined by two key numbers: the atomic number, which is the number of protons, and the atomic mass, which is the total number of protons and neutrons. These numbers help identify elements and their isotopes. Atomic mass is important for calculations in chemistry and physics, while atomic number determines an element's place in the periodic table. It's important to distinguish between mass number and atomic mass. The mass number is a whole number representing the total protons and neutrons in a specific atom, while atomic mass is the weighted average of all isotopes of an element. This distinction is crucial for understanding atomic structure and for performing accurate scientific calculations. When atoms absorb or emit energy, their electrons jump between energy levels, producing light of specific wavelengths. This creates atomic spectra, which are unique to each element. Scientists use these spectra to identify elements in distant stars and galaxies, as well as in laboratory analysis. Atomic spectra are like fingerprints for elements, revealing their presence even across the universe. Isotopes have a wide range of applications. In medicine, radioactive isotopes are used for imaging and cancer treatment. In archaeology, carbon dating uses isotopes to determine the age of ancient artifacts. Isotopes are also used in industry for tracing and quality control. Their unique properties make them valuable tools in science and technology. Not all nuclei are stable. The stability of a nucleus depends on the ratio of protons to neutrons. If this ratio is too high or too low, the nucleus can become unstable and undergo radioactive decay. Stable nuclei are found in nature, while unstable ones are often created in laboratories or during nuclear reactions. Understanding nuclear stability helps explain the existence of different elements and isotopes. Half-life of a radioactive isotope is the time it takes for half of a sample to decay. This property is unique to each isotope and is used to measure the age of rocks, fossils, and archaeological finds. Half-life is also important in medicine, where it determines how long a radioactive tracer remains active in the body. Understanding half-life is key to using isotopes safely and effectively. Nuclear fission is the process used in most nuclear power plants to generate electricity. When a heavy nucleus like uranium-235 absorbs a neutron, it splits into smaller nuclei, releasing energy and more neutrons. These neutrons can trigger further fission reactions, creating a chain reaction. Controlling this process allows us to harness nuclear energy for power generation. Nuclear fusion is the process that powers stars, including our sun. In fusion, hydrogen nuclei combine to form helium, releasing vast amounts of energy in the process. This energy is what makes stars shine and provides the heat and light necessary for life on Earth. Scientists are working to replicate fusion on Earth as a clean and virtually limitless energy source. One of the major challenges of nuclear energy is dealing with radioactive waste. Nuclear waste must be carefully stored and managed to prevent environmental contamination and health risks. Scientists and engineers are developing new methods for waste disposal and recycling to make nuclear energy safer and more sustainable for the future. While nuclear energy is generally safe, accidents can have serious consequences. Incidents like Chernobyl and Fukushima have shown the importance of strict safety measures and emergency preparedness. Learning from these events helps improve reactor design and operational protocols, making nuclear power safer for everyone. Nuclear medicine uses radioactive isotopes to diagnose and treat diseases. Techniques like PET scans and radiation therapy rely on the unique properties of isotopes to target specific tissues in the body. Nuclear medicine has revolutionized healthcare, allowing for earlier detection and more effective treatment of many conditions. Imaging techniques like PET and SPECT use radioactive tracers to create detailed images of the body's internal structures. These methods are invaluable for diagnosing diseases, monitoring treatment, and guiding surgeries. Nuclear imaging provides information that other imaging techniques cannot, making it a vital tool in modern medicine. Radiation is a natural part of our environment. We are exposed to small amounts of radiation from the sun, the earth, and even the food we eat. While high levels of radiation can be harmful, the low levels we encounter daily are generally safe. Understanding radiation helps us make informed decisions about its risks and benefits. Protecting ourselves from harmful radiation involves using shielding materials, limiting exposure time, and maintaining a safe distance from sources. In medical and industrial settings, strict regulations ensure that radiation is used safely. Advances in technology continue to improve our ability to detect and protect against radiation hazards. Nuclear weapons are devices that use nuclear reactions to release massive amounts of energy in the form of explosions. The development and use of these weapons have had profound impacts on global politics and security. Efforts to control and reduce nuclear arsenals are ongoing, as the consequences of nuclear war would be catastrophic. Spread of nuclear weapons is a major international concern. Treaties like the Nuclear Non-Proliferation Treaty, NPT, aim to prevent the spread of nuclear weapons and promote peaceful uses of nuclear technology. International cooperation and monitoring are essential to ensure a safer world for everyone. Research in nuclear physics continues to uncover new insights into the structure of matter and the forces that govern the universe. Particle accelerators and advanced detectors allow scientists to study nuclei and their interactions at the smallest scales. This research not only advances our understanding of the universe, but also leads to new technologies and applications. Particle accelerators are powerful machines that speed up atomic particles to high energies and smash them together. These collisions allow scientists to probe the structure of atoms and nuclei, discover new particles, and test theories about the fundamental forces of nature. Accelerators are essential tools in modern physics research. Scientists have discovered and created new elements by smashing atomic nuclei together in laboratories. These superheavy elements expand our understanding of the periodic table and the limits of atomic stability. Each new element brings new challenges and opportunities for research, pushing the boundaries of what we know about matter. Antimatter is the counterpart to ordinary matter with particles that have opposite charges. When matter and antimatter meet, they annihilate each other, releasing energy. Studying antimatter helps scientists understand the origins of the universe and why there is more matter than antimatter in existence today. Atoms are the foundation of chemistry. Chemical reactions involve the rearrangement of atoms to form new substances. By understanding how atoms interact, scientists can create new materials, medicines, and technologies that improve our lives. The study of atoms is at the heart of all chemical processes. Atoms are also essential in biology. All living things are made up of molecules, which are combinations of atoms. The way atoms bond and interact determines the structure and function of proteins, DNA, and other biological molecules. Understanding atoms helps us unlock the secrets of life itself. Modern technology relies on our understanding of atoms and their properties. From semiconductors in computers to lasers and medical devices, atomic science drives innovation. Advances in nanotechnology and quantum computing are opening up new possibilities, all based on the behavior of atoms and their components. Atoms are everywhere in the universe, from the air we breathe to the stars in the sky. The processes that create and destroy atoms shape the evolution of galaxies and the formation of planets. Studying atoms helps us understand the origins and fate of the cosmos. The study of atoms and nuclei is far from over. New discoveries in particle physics, quantum mechanics, and nuclear technology continue to push the boundaries of our knowledge. The future holds exciting possibilities, from cleaner energy sources to deeper insights into the nature of matter and the universe. We've covered a lot of ground, from the basic structure of atoms to the complexities of nuclear reactions and their applications. Understanding atoms and nuclei is essential for science, technology, and our everyday lives. As we continue to explore the tiny universe within every atom, we unlock new possibilities for the future. Atoms and nuclei may be incredibly small, but their impact is enormous. They shape the world around us and hold the secrets to the universe's most profound mysteries. By studying these tiny building blocks, we not only gain knowledge but also the power to shape our future. Thank you for joining us on this journey into the heart of matter.